Astrobot.
Hi, in this lesson we will discuss the so-called n-body problem, which is the most general problem of orbital mechanics. This model is commonly used for the prediction of orbital trajectories of celestial bodies or spacecrafts, basing on the applied forces. During the high school, we learned that the motion of an object is the result of the actions applied on it. Forces are responsible for translational variations of motion, and torques for rotational ones. We can identify the cause of a change in time of momentum of a point mass with the result of the summation of the forces acting on the point mass. Momentum is a vector, and forces have to be summed up vectorially as well. The same discussion holds for the rotational equivalent of momentum, which is the angular momentum. Its variation in time comes from the result of the summation of all the torques applied to the point mass. If we now consider two point masses in the inertial reference frame ijk, we can use this notation in order to refer to the position vectors ri and rj. We can also identify the vector rij, which corresponds to the distance between the point masses. This is the convention used in the video. I and j are indices representing a generic couple of point masses. Rij and Rji both represent the distance between I and j. The only difference is which mass we start from and which mass we move to. Similarly, Fji is the force caused by j and felt by I, vice versa for Fij. From the previous slides, one can easily find this relationship between Rij and Rji. In the following part of the video, we will assume gravity as the only acting force. As we know, gravitational forces are exclusively attractive and directed along the line that connects the attracting masses. Its magnitude is directly proportional to the masses and inversely proportional to the squared the distance between the point masses. But what happens if we have a system formed by more than two bodies? As we can see in this example, if we have 5 masses, we will have 4 forces per mass. The motion coming from the multiple interaction is often counterintuitive and very difficult to predict. After fixing velocity and position, we have this real mess. If we want to clean up this situation, we need to study the problem in more detail. This is what we obtain by summing up all the gravitational forces and torques affecting our n bodies. We can exploit this relationship between Rij and Rji to make things a bit easier. In this way, we have just Rij. Now, if we recall the definition of the distance between I and j, we can substitute this expression in the torque equation. Rj has then disappeared. If we remember what we studied in maths, we know that the cross product of a vector by itself is null. Rij then disappears from this term. We can then subtract these terms from the two equations, simplifying them a lot. We obtain two basic laws of mechanics. The variation in time of the sum of all momenta and the angular momenta of the system is zero. In other terms, the momentum and the angular momentum of the center of mass of the system do not change in time. The conservation of these two quantities is very important in orbital mechanics. Considering momentum, we can state that a uniform momentum corresponds to the simplest kind of motion, the uniform linear motion. Consequently, the position of the center of mass of the system in time can be written in this way. C1 represents the uniform velocity and C2 the initial position. The angular momentum can be considered a third constant, C3. There is one last constant that we can add to the collection. In order to do this, we need to go back to this equation. By definition of momentum, the left side becomes this one. We can multiply both sides by the velocity of the I point mass. The left-hand term can be rewritten in this way, thanks to the properties of derivatives. The right-hand term instead can exploit the fact that a gravitational force Fij is equal to the gradient of the gravitational potential energy Uij. By rearranging all the terms and by computing the sum of the potential energies in the right-hand term, we arrive at this stage. We can easily recognize the expression of the kinetic energy of the point mass I in the left-hand term. Analogously, we recognize the expression of the potential energy in the right-hand term. We can find this very compact expression. Since the time derivative of this subtraction over all the n masses is null, we have a new constant C4, the mechanical energy of the system. We began with 6 by n equations, corresponding to 3 translational and 3 rotational degrees of freedom per mass. Then we identified the 10 constants. In fact, since C1, C2 and C3 are vectors, they correspond to 3 scalar equations each. C4 instead is a scalar constant. If we have just 2 point masses, the subtraction of the constraints leaves 2 degrees of freedom. We will see in future videos how to deal with this situation in systems formed by 2 masses. Of course, if n is higher than 2, we have a higher number of equations, and no analytical solution is possible. Thanks for watching.